The 2.5D variational FDTD, also called the varFDTD solver, works by collapsing a 3D geometry to 2D and runs a 2D FDTD simulation, which is much faster and uses less memory compared to a 3D FDTD simulation. The method used to reduce the 3D problem to an effective 2D problem will be discussed in the solver physics section of the course. Because the solver is based on the FDTD method, and many of the settings and workflow for using the solver are shared with FDTD solutions, we will not be covering the shared features in detail in this course, and the FDTD 100 course is a recommended prerequisite. As mentioned, the advantage of the varFDTD solver is that it allows us to simulate 3D devices using a 2D FDTD simulation. This is useful for simulating relatively large devices where the dimensions of the device are hundreds of times larger than the wavelength, and for prototyping designs where you need to run many simulations to sweep the parameters of the design, since this will greatly speed up the process compared to running 3D FDTD simulations. A typical design process is to start by using the varFDTD solver for initial prototyping to determine a range of design parameters that optimizes the performance of the device, followed by verification of the results and extracting high-accuracy results using 3D FDTD or EME simulations. Assumptions used by the varFDTD solver limit the types of devices that can be simulated. The varFDTD solver is ideal for simulating devices where the light travels within one plane of the device, and there is no vertical coupling between different slab modes, or polarization conversion from TE polarization to TM, or vice versa. Photonic integrated circuit components, which are based on slab waveguide structures, are an example where the varFDTD solver works well, since they often support two vertical modes with different polarizations. In the following unit, we will go over some examples to show when the varFDTD solver can and cannot be used. If you are unsure whether your device meets the assumptions of the method, you can test a simple version of the device and verify the results by comparing with the results from a 3D FDTD simulation or an EME simulation, which do not require the above assumptions.